In 1827, a German high school teacher discovered what he called a pure law of nature. But when he published his findings, he was first ridiculed, then completely ignored. One professor said it was a web of naked fancies, and the result of an incurable delusion. Another said it was an unmistakable failure, and that anyone who preached such heresies was unworthy to teach science. The criticism got so bad, he eventually resigned his position and moved to another city 400 kilometers away. About 15 years later, though, the Royal Society of London would recognize his work and award him the Copley Medal, essentially equivalent to the modern Nobel Prize. And today, this same law is taught to teenagers across the world as the fundamental principle of electronics. Georg Ohm was born in 1789 in Erlangen, Bavaria, to a modest working-class family. His father was a locksmith who had no formal education, but loved math and philosophy with a deep passion. He educated himself to such a high degree that he was able to provide an excellent education to Georg and gave him a strong foundation in both math and science. Eventually, in 1804, Ohm went off to study at the University of Erlangen. This would last only 3 semesters, though. While attending university, he spent much of his time pursuing non-academic interests, to the dismay of his father, who withdrew his financial support and forced his son to drop out. Over the next decade or so, Ohm took up a wide number of math teaching posts in various cities across modern-day Switzerland and Germany. He was eventually able to finish his university degree and settled into a permanent role as a high school science teacher at the Jesuit Gymnasium of Cologne, a top-rated institution that was better than any Ohm had previously taught in. Most importantly, the school had something that Ohm would use to dramatically alter his life: a well-funded laboratory. Ohm began his teaching position in 1817. Around this point in history, the theory of static electricity was well developed. The understanding of moving charges, or current on the other hand, was still in its early stages. The units of a volt or an amp did not exist yet, and there was no consistent calibrated way to measure current. The prevailing idea about observed electric forces was that they consisted of the action of some sort of electrical fluid. There were 3 discoveries in the early 1800s, though, that fundamentally changed this understanding of electricity. And while Ohm initially used his school's lab as an aid to teaching, these 3 discoveries also convinced him to devote his spare time conducting research in the lab. And it enabled him to systematically study and experiment with electricity. The first of these discoveries was the battery, invented by an Italian scientist named Alessandro Volta in 1800. Volta provided a convenient, relatively easy way for scientists to create a continuous flow of electricity. All one had to do was take a stack of alternating copper and zinc plates. Between each layer, place a piece of cloth soaked in brine. This would generate an electric force, and by connecting the top and bottom plates with a wire, an electric current would be produced. Volta's invention came to be called the voltaic pile, and it was pivotal in the process of understanding what electricity is. Before this, scientists were only able to create temporary sparks. Now, scientists of all kinds were able to create a continuous electric current and use it to conduct experiments in entirely new ways. The voltaic pile would eventually allow Michael Faraday to conduct his famous experimental work that would lead to the 4 equations of electromagnetism. But before that, there was another pivotal discovery by the Danish scientist Hans Christian Ørsted. In 1820, after setting up a voltaic pile, Ørsted placed a magnetic compass nearby. To his surprise, he saw that the needle moved. After repeating the experiment several times with magnets in various locations, he observed that the magnets formed a circle around the wire. Somehow the current flowing through the wire was causing a magnetic force around it. The first link between electricity and magnetism was discovered. Both Volta's and Ørsted's discoveries played a pivotal role in Ohm's initial experiments with electricity. The third discovery, which I'll mention shortly, provided the final solution to some of the difficulties Ohm encountered along the way. Ohm began his experimental studies by first deciding to study the conductivity of various metals. Most scientists at the time were convinced that the voltage in a battery and the current that flowed in a wire were completely independent phenomena. Ohm believed otherwise. He was convinced that the two were linked by some physical law, and he was determined to discover it. He began by setting up a voltaic pile and connecting it to a torsion balance, an early form of an ammeter. Essentially, it consisted of a magnetic needle that would move more or less strongly depending on the strength of the current. He experimented with wires of different materials like copper, gold, silver, and brass. He also varied the lengths of wires, but made sure all of them had the same diameter. Ohm found that the following materials with their corresponding lengths were all equally conductive. But he couldn't find the deeper connection between voltage and current that he was really after. The reason? His source of power, the voltaic pile. Though Volta's invention provided a much needed advance in providing a continuous current to scientists at the time, the performance of these batteries was anything but perfect. The current quickly dissipated over time. In fact, when Ohm conducted his experiment, he used a standard wire as his control, and then he would switch various wires in and compare the current strength with it versus the current strength with the standard wire. There was a big problem though. The standard wire kept experiencing a smaller and smaller current over time. He decided to attempt to calculate what he termed as the loss of force here, and he came up with this equation. But after making slight adjustments and repeating this experiment a few times in different ways, he realized he needed a better method. The rate of decay of the battery was just too unpredictable, and the equation he initially found didn't consistently fit the data. At the suggestion of a colleague named Johann Christian Poggendorf, he decided to replace the voltaic pile with a thermocouple. This was the third key discovery that enabled Ohm to make his own scientific breakthrough. Now, before I explain how the thermocouple led to Ohm's breakthrough, I'd like to take a minute to thank this video's sponsor, Odoo. Odoo is an all-in-one management software that gives creators, businesses, and entrepreneurs tools to simplify their day-to-day management. They have a ton of easy-to-use applications designed specifically to meet all your business needs and streamline your workflow. If you need systems that handle taxes, invoicing, and sales, or even full website creation and more, Odoo can handle it all in one place. No more duct taping and having to manually coordinate between various apps. Just one streamlined system that helps you operate more efficiently so you can focus on what actually matters. And as your business or your team grows, you can easily add new tools. So Odoo can grow along with you at your pace. The best part is that your first app with Odoo is completely free for life, and it includes unlimited hosting and support. You can also try it risk-free with a 15-day free trial. No credit card required. Just click the link down below. Now back to the thermocouple. The thermocouple was discovered by a German physicist named Thomas John Seebeck in 1822. Seebeck found that if he made a circuit with two different metals, he could cause a magnetic needle to be deflected. In other words, he could produce a steady electric current. Crucially though, this only occurred when there was a temperature difference between the two. So one metal had to be either heated up or cooled. Heating would cause the needle to go in one direction, whereas cooling resulted in a deflection in the opposite direction. In order to use a thermocouple as his power source, Ohm had to slightly change his experimental setup. He began by creating his own thermocouple with bismuth and copper. He then placed two containers underneath, one filled with boiling water and the other filled with ice. This created a constant 100-degree temperature difference between the two. Finally, he connected all of this to two cups filled with mercury, and he also attached a torsion balance to measure the strength of current again. The cups of mercury were the means by which he connected the circuit. When he would place a wire inside the cup, the circuit would close and current would flow. When he removed it, the circuit would open and the current would stop. The thermocouple was exactly what he needed. It provided a continuous, reliable current. He then tested 8 wires of varying lengths and recorded the deflection of the needle for each one. He found the following results. Ohm then stated that the above numbers can be represented very satisfactorily by the equation x equals A over B plus X, where big X is the strength of the magnetic effect of the wire, little x is the length of the wire, and according to him, A and B are constants that depend on the exciting force and resistance of the remaining parts of the circuit. In other words, A and B depended on both the wire's material and the source of power. He then decided to make the temperature difference smaller to see how this would affect his results. He found that B was not affected at all by this change, but A was. Ohm concluded that A depended purely on the exciting force, and B depended purely on the resistance of the circuit. He had just discovered what we today call Ohm's law. In modern notation, we call the magnetic effect the current, A the voltage, and the denominator here is the resistance. Ohm wrote up all these results in a paper published in 1826. But he wasn't done just yet. You see, a few years prior to this, a French mathematician by the name of Joseph Fourier published a revolutionary book on heat that included, among other things, the invention of Fourier series and the heat equation. Ohm had been deeply impressed by Fourier's work and wanted to provide the same type of rigorous mathematical framework to the physical law he just discovered through experiment. He spent the next year developing a purely mathematical theory that made very little reference to his experiments. He then published his new theory in 1827 in a book titled The Galvanic Circuit Investigated Mathematically. In it, he described electricity very much like Fourier described heat. And he even mathematically derived a new version of his law that looks even more like the modern version today. But as I mentioned at the beginning of the video, this work was not well received by the scientific community surrounding Ohm. A prominent professor in Berlin named Heinrich Wilhelm Dove said it was a naked web of fancies. Another Berlin professor named Georg Friedrich Pohl called it an unmistakable failure, and even convinced the German Minister of Education to pressure Ohm to resign, which he ultimately did. All this occurred for many reasons, but to give you a bit of insight into why this seemingly strange situation came about, here are two factors that played a significant role. First, most German physicists at the time were philosophically opposed to mathematically deductive physical theories. They thought it wasn't an accurate way to discover and understand the laws of physics. What they preferred instead was a focus on performing experiments and letting experimental results guide their understanding of theory. It seems that the later mathematical theory that Ohm developed was the primary contact many had with his work, and they were unaware of his earlier experimental results. As a consequence, they simply did not appreciate its emphasis on math and lack of contact with experiment. The second reason was the way in which Ohm wrote. He seems to have lacked the ability to communicate his ideas in a clear way that others could understand. Though he began his treatise explaining all the math he was using, most of it was just completely unfamiliar and confusing to his readers. As one author wrote about Ohm's book, in neither the introduction nor the body of the work did Ohm bring decisively home either the underlying unity of the whole or the connections between fundamental assumptions and major deductions. After being forced to resign from his permanent position in Cologne, Ohm took up various temporary teaching positions at schools in Berlin. Eventually, in 1833, he was able to become a professor at Nuremberg Polytechnic. It was only after scientists from other countries discovered Ohm's work and began promoting it that he finally got the recognition that he deserved. In particular, William Surgeon and Charles Wheatstone, two scientists from England who promoted Ohm's ideas, as well as Claude Pouillet from France, who independently confirmed Ohm's results. This eventually led to proper recognition in his homeland as well. In June 1839, he became a member of the Prussian Academy of Sciences. Then in 1841, he was given the Copley Medal by the Royal Society in London, essentially the Nobel Prize of his day. And finally, in 1852, he achieved something that was his lifelong ambition. He was appointed the chair of physics at the University of Munich, which he sadly would hold for just 2 years as he passed away in 1854 due to a stroke. Years after his death, he would receive an honor that would make him ever present in the scientific community. In 1881, when the International Congress in Paris was establishing a system of electric units, they defined the amp, the volt, and the ohm. To this day, this unit of measurement, together with Ohm's law, are used by millions of students worldwide as the cornerstone of analyzing electrical circuits. If you'd like to see more videos like this, join my Patreon community and support the channel by clicking right here. And thank you to all the generous patrons who make these videos possible.